Okay, so now it is time to start. Next talk. The next speaker is Professor Chao Wang at the Peking University. The title of his talk is on the motion of interfaces of compressible and incompressible fluid with surface tension, a priori estimated. So please.
Thanks for the introduction, and thanks for the organizer for giving me the opportunity to give a talk here. So, today I will talk about the compressible and incompressible fluid with the free boundary. So yesterday, Professor Shibata and gave a talk to say something about the incompressible and the incompressible case. And the first talk today is given by the Professor Cooper. He talked about some compressible and incompressible case. But the different there's a difference between me and the other result is that here we can see about the Euler equations. Let me see that this is my schedule here. This is my system. That means let me draw a map. That's a free surface here. The upper is the upflow is satisfies the compressible Euler, and the lower fluid satisfies the incompressible Euler. So today I will want to show the priori estimates for this this system. So the equations I think because before other professors said a lot about that, so I just skip that. That's so the U is the velocity, the rho is density, the P stands for the pressure. The plus means the upper flow. The minus means no flows fluid. And this kind of problems, we have to deal with the moving domains. That means the surface is move as the fluid moves. So we have to deal with this ones. Like because the free boundary is unknown, so we need some boundary condition here. So the first line of here is means the normal of the velocity of the fluid is equal to normal the normal velocity of the free boundary. So the second one means that the normal the jump of the normal of the velocity is 0. Here we consider about the system is free boundary, the free boundary with substantial. But if there's been here, the sigma is a constant, we call the coefficient of the substantial. The kappa here is means that the mean curvature of the free surface gamma t. So that's some notations we have to we are used later. We here we can say about the 3D case. Of course, it works for the 2 dimensions or any dimensions bigger than 3. Here we will have to this condition means that the pressure of the compressible case is given by the function of the density. We assume that means sometimes the P plus is given by some function, for example, rho plus gamma. But we are here the gamma is equal, usually is bigger than 1, but here we assume that gamma is equal to 2. But if you consider about the general gamma, our method is also worked. So because here we consider about the strong solutions, so we don't meet the problems coming from the weak solutions. Here we assume that the compressible Euler equations is away from the vacuum. That means we assume that the density, the initial density, has the lower has a positive lower bound. Here we assume that's here. Because we just consider about the local hypothesis of the system. So when the time is very short, short, so very small, this condition can be also satisfied. Okay, so the this is notation if we use. Oh, here I have to mention that we assume this Sharper interface, the graph is a Sharper interface. The free boundary is a graph, but this is if we can see about the case like it's not graph. We have I think it's also works, but we have to use some methods coming from Shatan, and then we will expand later. Okay. This is our setting. So right now we can see some known results of the free boundary problem. First, we can see about the incompressible Euler. Here we mention the one-phase flow. That means this fluid is water is here. The upper fluid is empty, or this is air. So we don't care about the upper fluid. We just consider about this domain. The first result is okay. This model we has another name is it's called water wave. For this problem, the first there's a lot of works, and by now I think the local hypothesis and the global hypothesis for this model is well known, and the structure of this problem is very clear. I think the first breakthrough result is given by the Wu, Professor Wu. She proved the local hypothesis with the local hypothesis of the water waves if the Taylor condition is satisfied. After her work, there's a lot of work to work on the water waves. They use different methods and different opinion to study the water waves. For example, the crystal in the bag, they use the geometry structure to give the periodic estimates for the water waves with vorticity. But the results of the Wu, she assumed the vorticity of the vorticity equal to 0. So but later the crystal and Numerics they use the geometry structure to remove this one, and then then they also use the geometry structure to study this water wave equations with vorticity. And my advisor, Professor Ping Zhang and Professor Zhi Zhang, they use a Clifford algebra method to prove the waves vorticity. Of course, there's a lot of other results. For example, content scholar they use Lagrange coordinate to study this problem. There's a lot of other results. We just skip this one. Yeah, of course, there's if you consider substantiation, we also can get almost the same local hypothesis for the problem. Here we can see about the incompressible area. So if the vorticity equal to 0, we also can, this system can also have the global hypothesis. The first result is given also by the Wu. She proves that 3D have the global hypothesis. For the 2D case, she proved the system have the almost global hypothesis. And then later, for the 2D case, Iloscu and Alazan, they use the different method to prove the 2D case have the also 2D case have it's also global hypothesis. After their work, there's a lot of other works to study the waves. For example, with they consider about the different case. For example, they have the bottom. They also have the substantiation. The different kind of results they have to the different many cases have been studied. Except this one, this is the smallest. Even if we consider about the beach problem, for example, that's the bottom is here. The surface, the first surfaces can touch the bottom. Even for this case, the local hypothesis also the local hypothesis has been got it. So in the end, that's for the one phase flow, for the incompressible oil, this case is well is if we go back to the compressible case, that means this case here is the air. This is a fluid satisfied compressible oil. The results of the local hypothesis is also well known. If we assume the density is away from the vacuum, that means the initial density have the lower bound. The also can the Mazida, Columbia, Session, Lindbergh, Chihimi, Chen, Luo, they also use a different method to consider about the many different models. If we we can also consider about the compressible case meet the vacuum. That means the density is can equal to 0 on the free boundary, and away from the free boundary, that's the density is bigger than 0, is positive. And they also add condition that, for example, gamma minus so if the pressure is given by this one, that means that this one big 0. If this is physical vacuum conditions, under these conditions, Lindbergh, Content Scholar, Jiang, Masmoudi, Luo, Yang, Xin, there's a lot of people to study this problem. They also get the local hypothesis. Right now, I think, even if in this case, because the this condition is here, that means that singularity is when the there's a singularity come out when you can cross this when this system cross the free boundary. So but if we just consider this domain, this system also smooth, and except the results on the local hypothesis, there's some results on the global hypothesis. For example, Luo, Xin, Zhen, they consider this compressible level stores or the compressible Euler with at some damping terms. They can prove the global hypothesis. And in Guo, Heidrich, Jiang, they also can get the the global hypothesis for the compressible Euler with a free boundary if the initial data is around is close to some special background solutions, which is given by the Thomas series. That kind of background solution have enough decay rate, so that they can prove in this very special case. But if you can consider the general case, I think it's because the compressible Euler always can be proved if in the whole space can be proved blow up, so we cannot expect the kind of things. This is the so right now let's see the method developed by the previous results. Let's see that if we consider the incompressible case, because incompressible case have the divergence free, so all we need is the estimates of the tangential directive. Because we can see that gradient U can be decompensated by, in this case, the divergence U and the curve U, something like that. There's some coefficient, we just skip it. Because right now the divergence U is equal to 0, so we don't need to consider this case. The vorticity is here, but vorticity cannot bring any trouble. So that means if you of course you can assume the vorticity equal to 0. That means if we want to get the estimate for the gradient U, we always need the estimates of the tangential directive. But for the compressible case, we don't have the divergence free, so we need some more information for the divergence U. But from the Euler equation, we find that dt rho something like divergence U, or dt U something like gradient rho. So that means if you want to get the divergence U, we need the estimates of the dt rho. So that means we need, for the compressible case, we need to use the material directive and the tangential directive to recover the normal directive. Okay, this is the difference between the incompressible case and the compressible case. So, but if we consider the two-phase flow, that means the upper and the low, have the both have the fluid. That's a very that's a big difference between the compressible and the incompressible case. For example, if we consider the two-phase flow for the incompressible incompressible case. This case we also can call it test sheet problem. This problem is instability if there's no substantial. But if we consider the compressible case for the 2D, here we just it means that for the 2D, this case is stable when the Mach number is bigger than square root of 2. So that means the incompressible is instability. Compressible is stability. So that means that's a very strange things. So so we just we want to consider that if we can consider the upper is compressible, the lower is incompressible. In this model, what kind of things will happen? But that's another thing I have to mention that is for the compressible case, two-phase flow for the compressible case, the proof is based on to my knowledge, the proof that's only one proof is okay. That means it's like that. The almost all the proof for the two-phase flow of the compressible case is based on the Nash-Moss iteration. So there's no proof based on the energy method. And there's only one paper I know that is given by the Stephen Ben. He proved that the case compressible and compressible case with the substantial. He used the energy estimates to prove this the local hypothesis for this model. Of course, that's so at the beginning we want to prove that the compressible case without the substantial, we want to use the energy method to prove this case, but right now we don't know how to do that. We just talk about with the other peoples. Maybe if we can consider about the compressible MHD equations systems, maybe we can use the energy method to prove this two-phase flow. This is to right now. I think I know. Okay, so this is no results. That's from now on we can see the main idea of our proofs. Now we focus on the case of the compressible and incompressible case with the substantial. So before we give the priori estimates, we give the definition for the energy function ET. ET is I'm wrong. ET is given by this one. Here we can see that the ET is just like H3, the H3 space. But from this definition, we can find that if we take one derivative on the partial t on the u or p plus, the regularity for them will lose 1. So this is a regularity for the velocity and the pressure, and here it means that regularity for the free surface eta. The eta is belong to H4. If we take one derivative, one partial t on the eta, that means the eta will lose one regularity on the space regularity. From the definition of the ET, we can know that partial t and partial x almost have the same positions. Okay, okay. The low order energy estimates is given by this one. This one is this function is used to close the energy, so we can skip this one. This is our main result. This is given by this result is done when I visit the University of the Hong Kong, the City University of Hong Kong. We discussed with Professor Luo and Professor Hao and Professor Gui. This is our results is very easy. This is a priori space. Based on this results, we give the confident that we can prove the local hypothesis. But as we know that even if we get even if we have the priori estimates for the free boundary problem, it's also difficult. It's very difficult to prove the local hypothesis. But we are lucky that Sheta and Zheng give the geometry structure for this free boundary problems. We believe that if we get the priori estimates, then we follow the method given by the Sheta and Zheng, we can get the local hypothesis. So this is I think this is technical problem, even if this is not easy one. As we see that if we consider the water wave problems with the substantial, that means that the partial t have the same position is like this one. That means this is because this thing is well known in the water wave equations with substantial. But here, as I said before, that we define this kind of energy functions. That means the partial t is have the same position, the same position as the partial x. This is simply not is not right. So we want to use the substantial to recover this quality. Let's see that if we can get that. Before we do that, the first thing because in our energy we don't have the estimates for the P minus. Of course, as we know that P minus is given by the incompressible Euler, so we can use the incompressible Euler. We can get estimates for the P minus. For example, we can use the equation of the incompressible Euler, so we can easily get that P minus have the same estimates for the have the same regularity as U minus. But we have to mention that in our energy functions, we have the estimates for the 3 times partial directives on time. For we have the estimates, we have the bound for this one, but for the P minus we don't have this quantity. We because this equation given by the incompressible Euler, we cannot have this estimates for this one. But if we can see about the compressible case, these things can be easy get, because this is the one part of the energy functions. So this number is so first thing we recover the regularity for the P minus. Then we improve the regularity of the free surface according to the due to the substantial. So with because of the boundary condition for the jump of the pressure means that the P minus minus P minus equal to the kappa, but we can use the we can rewrite the we can write the precise equation of the mean curvature is equal to this one. This is the elliptic equations, but the P minus is you use the trace theorem. We have this regularity. This one is elliptic equations. That means that we have the either belong to H 4.5, but according to our energy functions, that means either equal to H4. So we have improved the regularity of the free surface. In other words, that of course this is this is the estimates for the space regularity. Then we can, if we take the partial t on the both sides of these equations, we can also get the equation, the estimates for the partial t gradient either, the estimates for this one. Of course, we can take 2 times the partial t on the both sides on this one, but we have to point that because the P minus we don't have, we almost to take the 2 times the derivative on the time, so we have this one. We only can have 2 times the derivative 2 times derivatives on the time. Only have this estimate. But if we here, as I said before, that from this lemma we find that we can get more 1/2 more regularity for the either. That means if we don't we just to see this one, because we have this means if we can consider that this one means according to the water waves with the substantial, this partial t have the same position as this directive. That means but on the other hand, according to our energy function, partial t have the same position as partial x. So if we don't take the time t, we only take the time, the derivative on the space. We take the space derivative. That means we should have 1/2 more regularity for this. So, but we don't achieve we don't get more regularity for the either, but we only we have achieved 1/2 more regularity for the either. So that's I think this for if we consider about local hypothesis, we have 1/2 more regularity. This is very happy things. Okay, this is improved regularity for a surface. Okay, this is things we can. Another thing is that if we can improve the regularity for the velocity, so next time we improve the regularity of the velocity, which is motivated by the water wave equations. First, we recording the equation of the either. So because this things is tangential to the free surface. So that means that dt either equal to okay, let me see b vb is means that u minus or the trace of the u minus on the free boundary. Okay, so then if you take the derivative on the both sides on these equations, we can get these equations. These equations can be written in this formation. This formation seems is not, because this here the left hand of these equations have one half more relative. That means u theta have the one half more relative. So that means next we will use u theta to recover the velocity. But the u theta seems is very since it cannot be recover the velocity, is very complicated. But according to the wave problems, we can rewrite the u theta as the following. We can get this one. This two. G, this is, you can be written by the Dirichlet-Neumann operator. Is like this one. This term is given by because of the vorticity. Of course, you first things we don't you don't worry about the vorticity will bring more trouble to you, because the omega and the dt omega have the same regularity. So that means if you take the dt on the both on these terms, this term will never lose regularity. So this term is okay, we can down. So the main term is this one. This one is we have to study the Dirichlet-Neumann operator, this which have been studied in the wave equations. Okay, Dirichlet-Neumann operator means that if we give is actually it's very easy, because this means that if we given you a harmonic functions, the boundary condition, if we give the boundary condition for our harmonic functions, we can get the normal derivative of the harmonic function on the boundary condition. That means the Dirichlet-Neumann operator. But the good thing is that the Dirichlet-Neumann operator have some is positive operator and self-similar operator. Then if that means u theta is equal to this one, we can introduce another good unknown. We use the Bernoulli decomposition. That means we can this operator is defined by the Bernoulli decomposition. Then means that we can introduce ui is equal to this ones. That means this one is like j either ui, something like this one. But this one is a positive operator. Then we can take the inverse. So that means we can recover we can prove that the ui, this means here, have the good regularity, have one half more regularity here. Then this is if we write the theorem is as following. Then if we get ui, how to go back to the u, you go back to the v or b, then we can go back to the u minus. That means. But if you have the u, we can just see that you can use the here you can by the this step is well known in the wave equations. If you get the regularity for the u, we can go back to the ui and b. Then we can, because we then we can go back to the u minus. This is As a result, we can get that because we can U minus belong to H3 on the domain. That means VB is belong to H2.5. But we can find here that if we, of course, from this one we can set. From this one we cannot cannot see any improved regularity. But from this term we can see that dt U is belong to H1. That means dt U belongs to H1/2 on the boundary. That means that VB is belong to H1/2. But here we can get get more regularity for the V and B. If we can get if we based on this lemma, we can improve the regularity for the P minus, as we said before. Now we have to improve the regularity for the velocity and the free surface. Then we go to the NG estimates. So the NG estimate is very easy. We just multiply the U then and integrate by parts. We can get the results. Let's see that. Because that's have boundary, we only can take the tangential directive. Here we use the TI. This means the is given by this one, and this bar partial means the tangential directive of the free surface. Then we get the first. We can get the here we only focus on the highest order estimates. So we take the 3 times directives on the both sides of the compressible equations. Then we here we have to convince that this reminder is the commutative of these terms. These terms are the low order terms because the commutated is have one directive, can recover one directive. So these terms are the low order terms. Then we take we also acting TI on the both sides of the velocity of the compressible oil equations. We get these ones. Then we can use the NG methods. We can get this estimates. That's it. But here we have the U because here we use this TIU plus. We are use the integrated by parts. We can cancel these terms. If we use integrated by parts, this boundary condition comes out. This is we will main difficulty in our proofs. For the by the same argument, we have the NG estimate for the U minus. This is boundary condition come out. So these terms, this remind terms is I think it's very easy to prove. This can be controlled by the NG function. So we have to deal with these terms. These terms we are give the estimates for the either, but it's not very easy to prove these ones. Let's see that for example, because this have jump for the P and the U, so we have to choose. We have to write the red part as following. We use the jump of the P is equal to kappa, so we get this. This is the main terms. This is but. You see that the TI is means three times the directive. This one is belong to H. This one. This means belong to L2. So this two terms. This commutated terms is not easy to cross. We will discuss later. But even if with these terms, is also easy to prove that. But as we prove that if the we have got the more regularity if the time directive on the is not too much, so we can improve the regularity. Based on these terms, for example, if we can support T0, means that 3 times directive on the space. This means in these terms, because we can recover, we get 1/2 more regularity for the either. This term can be estimated like this one. So these terms can be controlled by the ET and the energy functions. So by the same argument, the T1 and T2 is also the same. So the biggest trouble is come from the T3. This part is the most difficult part. Because there's too many time directives in this case, we cannot use the lemma 3.3. So the first thing that we have to change the time directive to the space directive. So we use the evolution equation for the either. Again, we can use these conditions. That means that we can get the dt kappa is we equal to this one terms. That means we can change the dt to the partial x. So we can get these terms to free. And in the end, we get this formation, but the remainder is contain the leading order is this terms. So we can go back to this problem. The boundary condition is given by this one, because this one is given by this one. So it's very easy to prove the leading order term is this one, because it's the same. So all we need is to deal with this one, because this term is belong to actually minus 1/2. R1 is also belong to L2, so it can be not controlled by the energy functions. To do this ones, we just to prove the leading order terms like this one. We just need put the leading order terms that out of like this ones. So we change these terms to the partial t. We use the evolution equations of the eta. We can go this one equal to this one, and because the dt eta something that like this one. So we can change the we can split the proof to I1 and I2. To prove the I1, we have to actually we can use we can take time priority out, put the priority out, then we can another terms come out. But these terms can be rewritten as partial x and partial. F is a smaller function, so we integrate by parts here, so we can cross this one. But for these terms, because this one is belong to L2, this one belong to H1/2. So this term can, according to the leading the energy functions, this one is lower order terms. So we can control by the energy functions. So we use these observations, we can cross the energy. So the I1 we can prove that like this one. So for the I2 can be done by the same argument. So all we need is to give the estimates for the commutator. For the commutator, we have to deal very carefully. So we can rewrite the commutator. We just put the worst part. That means Ti is equal to dt3. So if we use this one, we can use we can change this term equal to we have to use that the norm the norm of the velocity, the jump of the normal velocity is equal to 0. So sorry. So this term we just focus this one. This ones we can use. This is just the tangential terms of these ones. Then we can use that this one is equal to this one. So for this one, that means dt3 means that we can have these factors. We have like this one. Then we can means that we can use the incompressible path. That means we can change we at beginning we use the boundary condition. Boundary terms. We can go back to the omega. So we can cross the energy here. So we just skip the proofs. I'm sorry. Okay. So my talk is here.
Okay, thank you for nice talk. So now time is for question or comment. Do you have any question or comment? So please, okay, please, Professor.
Thank you very much. It's very good, very nice. By the way, I think maybe your boundary was your free surface is rather close to the flat, isn't it?
Sorry,
you don't have the first eigenvalue of the Laplace operators.
Pardon?
Do you have a first eigenvalue of Laplace Bertrand operators? Because you consider the surface tension.
Yeah.
But maybe you consider the flat surface, right? Like very close to the flat surface. Therefore, you don't need any. Because I consider the ball like close to ball. Then of course I consider the not Euler, I mean Navier-Stokes. But anyway, from surface tension, I have the first eigenvalues of the Laplace Bertrand operators from the capillarities. So your case is maybe half space. No, sorry, some flat spaces. Therefore, you don't have any such.
You mean that if I can say about this case, for example, this one, right?
Yes.
I think because here we can say about local hypothesis. I think we can. I didn't I think it's maybe we can. This model can also work because here we can say about Euler equations, not Navier-Stokes equations. So I think in your work, your talk given by yesterday, you can say about the Stokes problem. I think it's more difficult. It's very different from this case. I think if we can say about this case, it's also can.
But this case is you have to seriously work on first eigenvalue of the eigenvalue of the Laplace Bertrand operators of the surface.
I didn't.
Therefore, you need for example, you have to work on the barycenter, and then you need the first energy inequalities.
Yeah, you're right. If here we assume that we have the very
maybe the surface tension gives you the much better decay.
Yeah.
Anyway.
Yes, because here we have
maybe a little bit different ideas you need, I guess.
Yeah. This is very different. Yeah.
Okay, but anyway, thank you very much. It's very interesting. Thank you.
Thank you. Thank you.
Okay, so next, Professor Watanabe, please.
So I have one short question that the aim of this talk is to derive the a priori estimate.
Yeah.
And so you assume that there exists a smooth solutions to the system.
Yeah.
And as far as I see your slide, you assume the existence of the velocity and the pressure. So do you assume the existence of some nice eta as well?
Yeah. Here, assume all of them are smooth. So we don't just priori estimates. We assume all are smooth. So.
Okay, thank you.
But if you want to prove local hypothesis or existence, it's another story, I think.
Thank you so much.
Do you have any question or comment? So I have one question. You introduced some instability result for two-phase incompressible flow without surface tension.
You mean the voltage sheet? Wait a moment, I can make it clear. You mean here?
Yes, yes. This is yes, two-phase flow for incompressible case. So what kind of instability happens without surface tension?
Because in this, without surface tension, this thing is also can be called voltage sheet problem. This we can change the system to elliptic equations. We can change this system to the elliptic equations with some initial data. As we know that elliptic equations is smooth. So if we also can prove that the solution is analytic. So if you give the initial data, it's not smooth or it's not analytic. Of course, this system we are is instability. So this means that they change these things to, for example, I didn't write a very clear things. For example, give things something like this. From here we see. Oh, sorry. This is F, and you don't care about the things on the F. This is elliptic equations. This is elliptic equation. You cannot give the initial data, even if this is a partial t. So because is elliptic equations is smooth, we can prove that. We just forgot this one because when we solve this elliptic equation, we don't need this condition. We can prove that U is C and is analytic. So, but if the initial data is not given, smooth is the T is belong to R. So the initial data is not analytic. Of course, this system is hypothesis.
So this is not physically instability, just illposeness of math.
Okay. You can see that.
Okay. Thank you. So do you have any question or comment? So if not, let's thank speaker again. Thank you. Thank you for nice talk.
Thank you.